Okay, good morning, everybody. Good afternoon, depending on where you are, I guess. This is the second part of the 6Xonline introduction. As Tommy mentioned, part one is on our website from February the 10th. And if you want to go review that, ridgewaykitesoftware.com. I got the contact information and the website details later on in the presentation for you. So my name's Peter Foster. I work for Ridgeway Kite here in Houston, doing technical support on the simulation product. This presentation will be a combination of PowerPoint and an online demo of this 6Xonline application that we're talking about. It says 60 minutes here, it's maybe 40, 45. And as Tommy said, any questions that you have, plug them into the online chat and we'll get to them at the end, or wait until the end and then just, ask when he unmutes you. Okay. So this is an introduction to both the 6X simulator and the 6Xonline app. Back on February the 10th, we showed some examples of what 6Xonline can be used to do. The presentation's available on our website. Today we're going to build on the examples that we showed then, and we're going to look at an example where we use a 24-stage well and we vary the pumping rate and therefore the job size and evaluate the recovery for a few different rates. So that's going to show how we can use the software to evaluate a range of operational choices and see their impact on the production. And it's also going to kind of point up the fact that the model needs to be realistic for it to give us meaningful feedback. And then going on the topic of the model being meaningful and realistic, we're going to then look at another example where we iteratively vary the enhancement parameters, which we'll talk about in a minute what those are, to bracket and then focus in on a calibrated match to a set of historical data. So that's our second example that we'll look at. So 6X, the reservoir simulator, integrates a flow simulator with the essential parts of a frac design model and a geomechanics solver into a single end-to-end workflow. It uses a geological model, which can be a simple layer cake model or a full-featured geomodel from Petrel or any other modeling package. It uses the fluid properties, the PBT data for the hydrocarbon fluids, and that can either be a three-phase or two-phase black oil model, or it can be a full equation of state compositional representation of those fluids. We also start with a stress state, so we need to know the current stresses and what the minimum and maximum stresses are, basically. So what we're going to do is we're going to model the life cycle of one or more wells all the way through from the pumping schedule, through the flowback and the production in a single run. And we're going to capture the interference between any wells, between stages, between clusters within a stage to get a realistic dynamic model of what happens when you fracture a well and then when you fracture another well nearby, and take into account the depletion and so on. So that's going to allow us to model things like the well location, say the well count, the placement, the landing, and the spacing of the wells. And that takes into account the stress shadowing, the depletion from nearby wells, and also interference brackets between wells. It lets us model things like the effect of completion design decisions, such as the stage count, the cluster spacing, and as we'll look at today, the size of the job. It also lets us build up to very sophisticated workflows, such as enhanced oil recovery design pilots for huff and puff injection schemes, and also full section implementation planning, where you're cyclically injecting into several wells and investigating how much to inject, how long to leave the well to soak, how quickly to flow back, all of those parameters. So that's the simulator. It's got a lot more functionality than we support through the online app at the moment. So 6Xonline supports a basic set of workflows. It allows you, it gathers you through gathering the data, building a layer cake model, inputting all the PVT and the stress data and so on, and setting up the wells and the fracking operations, through to collating all that data into a simulation case, submitting that simulation case to either a cloud or a local server, and then retrieving the results and analyzing them as line plots. So the cases that are built, as I say, they're a basic subset of the functionality, but you can also export those cases and use them as the basis for much more sophisticated models, all the way up to and including enhanced oil recovery full section models, as I mentioned before. So what do we mean by it integrates the flow with the frac design and the geomechanics? Let's have a little look at how we achieve that. So the first input that we need is a geomodel, and on that geomodel we need to know what the stresses are. So as I said, that geomodel can be a simple layer cake like we'll see created today, or it can be a full-featured geomodel from Petrel. The stresses that we need are the minimum and maximum horizontal stresses and the vertical stress. Optionally, we can also put in a rock strength parameter. And then the simulator will use that basic model plus the information that we give it about how the stages are treated, how much is injected, where along the well, and it'll use these enhancement parameters to work out how the fractures propagate through that geomodel. The first parameter is the pore volume expansion, which controls how the fractures open in terms of their total volume. The second one is the tensile enhancement, which is an amount of permeability that is to be added when the rock breaks. So we give the maximum amount of permeability. We also give the maximum amount of shear that will be added to enhance the matrix fracture interface to allow leak off from the fractures into the matrix. So those three things go together to determine how the fluid will move through the fractures, leak off into the matrix. And between them, they control how long the fractures become, how much fluid is absorbed off into the matrix, whether or not that fluid can come back, and so on. We also use a residual connectivity parameter, which controls how the fractures close as we deplete the reservoir. So when we start the flow back, the pressure will drop and we will lose some of that enhancement that we input, and the rate at which that enhancement is reduced will be controlled by this residual parameter here. Okay, so if we look at that on a graph, what's going to go on? So here we're plotting the pressure or the stress on the vertical axis and the distance from the well on the x-axis. And along the y-axis here, we've marked the point at which we have the initial stress, which needs to be overcome to achieve that breakage. So at the cluster at the well bore, we're going to start at the origin point here. And as we pump into that cluster, the pressure at the well is going to rise, and that pressure front is going to push out into the reservoir some distance. As we pump harder, we are going to breach the initial stress state and cause breakage. So as we reach into this zone up here, we will apply a certain amount of enhancement to all the parts of the model that correspond to that. So we'll apply those two types of enhancement that we talked about: the tensile failure, which is represented as a permeability of the fractures, and the shear failure, which is represented as the matrix to fracture interface, the leak off between them. So anywhere where we have broken through the initial stress, those things will be enhanced. Depending on how much we get past, how much net stress we achieve, how far past the initial stress we go with the pumping, the higher we go, the more enhancement we'll get, up to the maximum, which was the input value that we gave it. Okay, so anywhere that's in this triangle here is going to be part of the SRV. And the distance that that reaches out from the wellbore, which is this line here, gives us the half length of the fracture that's coming off of that location along the wellbore. Now, as I said, this can be happening in a full-featured geological model. So along the well, each cluster within each stage can be behaving differently. The half length may vary from place to place. The amount of enhancement can vary from place to place depending on the underlying parameters of the rock itself. Okay. So if we look at a single point somewhere in that SRV, we can plot the pressure against the permeability. So this red line here is our pressure. So it starts off at whatever the initial pressure is, and then it rises abruptly when we start pumping the fracture. At some point, we breach that initial stress and we achieve a pressure that corresponds to a negative stress, negative net stress. When we've achieved that, we start adding in permeability to model the enhancement of the fracture conductivity. The more pressure we apply, the more negative net stress we get, and the more permeability we add. So at some point we get to a maximum permeability, a maximum amount of enhancement. Now remember, this is what we're showing here is the permeability in one of the directions. This is happening in the X, Y, and Z direction simultaneously for the permeability, and it's also happening in the matrix to fracture interface direction by enhancing the shear in a similar way. Okay. Now, we then close the stage, stop pumping, and the pressure will stabilize some. And then when we start to flow back, the pressure will drop. As the pressure drops, the permeability will also drop, and the rate at which the permeability drops, the rate at which closure occurs, is going to be governed by that residual value that we supplied. So if we drop the pressure by 10,000 from the maximum that we achieved, we will retain whatever percentage of the maximum permeability we added based on that input number. So if we said 20%, then we will achieve a certain amount of permeability, and we'll keep 1/5 of it after the pressure has dropped down by 10,000 psi. Okay, so that's the way that the enhancement and the propagation is happening inside the model. Let's take a look at how to set up some examples that we can use that with. So first of all, we're going to look at this treatment rate sensitivity example. So we're going to use a 24-stage design, similar to previous examples from the presentation back in February, which, as I say, you can go back and review on the website if you want to see that. So we can pump at a range of rates, and the rate at which we pump will determine the total job size. So we're going to pick 3 different rates, and we're going to try each of them in turn to see what our results look like in terms of the recovery. There's some information down here about the model and about the well. Basically, there are 2 geological units to it, which have slightly different parameters. And we put a 10,000-foot well across close to the bottom of the upper unit. And we fracture that with 24 stages at 30, 40, and 50 barrels per minute. So let's go look at the app and see how that's set up. So this is the app itself. We've got 3 columns of options here. The first one is just the welcome screen and the help pages. The second one governs the major sections of the application where we create the models by collating the data together. We submit runs to either local or the cloud, and where we analyze the plots from the runs. So one thing that we can do here is we can load in a pre-prepared model. So let's load this one in and take a look through it. We've got some notes down the right-hand side here, which correspond to the information about the geology and the structure and so on that we saw in the slide. So within the data collation section, we've got data pertaining to the reservoir, to the wells, to the frac jobs, and to the scenarios, which is basically the time-dependent implementation of the operational settings within the context of the geomodel. So if we look at the reservoir, we've got the kind of the overview of the formation on this tab. So we've named our reservoir. We've got a top depth for it of 9,000. If we hover over any of these input panels, it'll give us a little bit more information, including the units that it's expecting. If you're in Canada, you can go to the options over here, and you can choose to use metric units. We'll stick with feet for today. So we've got our top depth of 9,000 feet, and we've got a pressure of 7,200. And that pressure applies at a datum depth, and the datum depth automatically corresponds to the well that you put in, whatever the depth of that is. We've also got the contact locations. These are set so that we're, in this case, fully within the oil zone. So the gas is up above us and the water is down below us. As we plug these things in, the picture down here in the little 3D cartoon here will update to show us what we've entered. So it's a simulation model, so of course we need our PVT. The application only supports black oil PVT, even though 6X itself supports an equation of state. There is a built-in light oil, which is based on a fluid from an Eagleford well, which you can use, or you could import your own PVT data with this button here. We also give it the bubble point pressure to go with that PVT. The stress field is input here. So we've got the minimum, the maximum, and the vertical stresses for the whole model. On this panel, the layer panel, we define the thicknesses and the characteristics of the geological units. So as I said, we've got 2 of those. The one at the top is 100 foot thick, and the one at the bottom is 120 feet thick. We're subdividing them each into 5 layers of simulation grid cells to do the numerical processing. Now, the geological characteristics of those units are defined here, where we have this rock lookup. So we can choose which set of rock data we use for each of the layers. We're using a different one for each. Now, what is included in that rock setting is set up on the remaining panels here. So on the rock panel, we've got a list of those available sets, and each set contains 3 items which are set on the remaining panels. So for rock 1, which goes with the top of the structure, we've got porosity 1, geomechanics 1, scal 1. And for rock 2, we've got all the same stuff, except we've got porosity 2 here. So we've got a different set of porosity. So of course, if we go to the porosity perm panel, we see here that we've defined 2 different sets of data. So the bottom one has a porosity of 0.05 and a permeability of 401. The top one has the same permeability, but a lower porosity. So those are tagged on to the geological units. The geomechanical parameters that are defined here are those enhancement numbers that we talked about. The maximum amount of permeability that's going to be added to represent the conductivity of the tensile fractures, the maximum amount of shear which is going to be added, and the compressibility in microsips, the rate at which the rock will expand when it breaks. The final 2 parameters here are the residuals that I mentioned. So internally, the simulator is going to decide for itself which rock is propped and which is broken, but then not propped. So we can give a different residual for each of those. So we're saying here that the residual in the unpropped rock is going to be 0. So essentially those fractures are going to open, and then they're going to close again as soon as we start to drop the pressure. In the propped region, we're going to retain 25% of whatever permeability we achieved, which will be based on a maximum of 1000 millidarcies here. Okay. So these parameters control how the rock breaks. The stress parameters control what pressure you need to achieve to get the rock to break. Over here on the end, we've got some relative permeability data that pertains to the matrix. We're not going to worry about setting that. We'll just use the defaults there. Okay, so all of these inputs make up the geological model, this simple layer cake of 2 units, one at the top, one at the bottom. Then under the wells tab, we can create a well, we can say what depth it's at and how long it is. Optionally, we can orient it relative to the stresses, so it doesn't have to be parallel to the minimum stress, but perpendicular, but it can be, and we'll leave it like that. It can also dip at some angle. We're going to say it's perfectly horizontal, so it's at 90 degrees to the vertical. Okay, so that's all we really need to define our well. And if we look at where it is on our little cartoon here, we can kind of see that it's close to the bottom of the top unit, which corresponds to that depth that we gave it of 9080. On that well, we can define some frac jobs. So each frac job set that we define is going to be a different experiment, essentially. So we've got 3 different frac operations defined, and they're named corresponding to the rate that they're going to pump at. But you notice that there's no real difference between them in terms of how many stages they have and how long the stages are. The difference is this parameter over on the right-hand side, which pertains to how the stages are going to be treated. So if we go to the stages panel, we've got those set here. So the 30 barrel per minute stage is going to be pumped at a rate of 30 for a duration of 3 hours. And then there's going to be a 3-hour gap. So when we start the pumping, we're going to push fluid into the stage, out through the clusters into the geomodel at 30 barrels per minute. And we're going to do that for 3 hours. Then we're going to shut that down. We're going to wait for another 3 hours, which corresponds to the time in the field that you're doing the wireline operations. And then we're going to start that next stage. We're going to do that for a total of 24 stages along the well bore. Okay. Now, each of those stages is going to use an injection fluid that's defined over here. And it's called SW for slick water. And we've put in a viscosity of 0.5. So the pumped water can be a different viscosity to the reservoir water. We can model that. We can also model the addition of propants. We'll cover that in a later session. We're not going to do that today. We're just going to use the internal triggering mechanism to determine which parts are propped and which ones aren't. So we've got all of our physical things here. We've got our reservoir, we've drilled our well in it, and we know how we're going to fracture that well. We need to set up a scenario that ties all those things together to a time sequence. So we've got a different scenario for each of our frac characteristics. And that scenario consists of a schedule and the well that schedule is going to use, and the frac job that is going to be applied to it. We tell it what time to do that frac job at. In this case, we're saying right at the start of the run, time 0. And then we've got a set of production criteria that govern the flow back. So those production criteria are going to kick in after 20 days, and they're going to be set on this panel here. So we're saying that the minimum bottom hole pressure is 1,000 PSI, and the target rate is 2,000 barrels a day of liquid. We're going to run for 4 years, and we're going to cut the well if it drops below 20 barrels a day of oil. Okay, so those are the time dependencies of the things that we're going to model. We use the build panel to put those things together into a case. So the case called something 30 uses the reservoir, the well, the frac job definition, and the scenario that points to the stage definition that corresponds to 30 barrels a minute. So we've got one for each of our setups, and the difference between them is which scenario they use. If we do check and build, we build that simulation set. It tells us if there's any warnings or errors. In this case, there are some warnings basically saying that we have some data that we're not using, which is kind of what we wanted anyway, so we'll not worry about that. We can show the keywords that are associated with that model. And if we wanted, we could save these keywords locally and modify them to do more sophisticated things, as I said earlier. But right now, we'll just stick with running these within the application. So to do that, we go to the Run panel. We pick the model that we want to run, and we submit it. Let's just log in here. Sorry, excuse me. This system isn't logged in because we had power failure and an internet failure here in Houston, and I had to switch to a different one. Okay, so when I logged into the remote server, it can now see all the jobs that I've ever done. And it turns out I've actually already run the 3 variations of this particular example that we've been talking about. I got them through last night before we had the power cut. So they are already here and finished. So we can skip the step of submitting them and waiting them to finish, and we can go straight to plotting. So if we go over to the plot panel, we can do Get Model and click on the summary data, the line plot data for each of those models. So the 30 barrel per minute one, the 40 barrel a minute one. Oops, accidentally double clicked, sorry about that. And the 50 barrel a minute one. So here are our recoveries, or our rates that we achieved. So depending on how hard we pumped the stages, we got different lengths of plateau and different amounts of recovery. So we could switch this from rate to showing production total. And you see, once they start going off plateau, the rate at which we're getting oil back is declining. So the more we pumped, the more we got back. However, the whole point of the model is to be able to work out what the right amount to pump is, not just to say, hey, you can pump as much as you want and you'll get better recovery. That wouldn't do us any good because it's not realistic. So if we go in here, we can take a look at the well water injection rate, which is here, and we can plot that for each of the runs. Now, you see here that we were only injecting for a very short time at the start of our 4 years. So we need to zoom in on just that period and see what was going on. So here's our stages being pumped. Let's take a look at just a few of them. Let's look at the first 2 days. So here's our first 2 days of pumping our well. The red one is the 30, the blue is the 40, and the green is the 50. And if you look closely at the one where we requested 50 barrels per minute, which looks like it's 72,000 barrels a day equivalent, we're okay with pumping that for a little while, but then it kind of gets backed up and it falls off. We can't maintain that rate through the full 3-hour pumping schedule. So we're not really pumping in the full amount that we were asking for. The model is limiting how much we can pump. So that's kind of an interesting result because that's what we want it to do. As I said, we don't want it to keep taking fluid and giving us more oil with no diminishing returns. So if we go back to our presentation slides, this is the kind of thing that we're seeing here, where with the high end of the injection rate, we couldn't quite get that into the rock. So what this shows is how important it is for the model to be realistic and calibrated so that it matches reality. And the way that we do that, like with any other simulation model, is by doing a history match. So that's what we're going to look at next, is tuning some of those parameters to get a historical match. Okay. So we're going to use the 24-stage well again, and we're going to assume that we've actually produced that well after fracking it. So for the frack program, we're going to use 45 barrels per minute based on thinking that that was probably the most we could achieve. And then we're going to look at the production parameters for that. We'll look at what we got back, and we're going to try and simulate it. So we're going to take the observed data from the field well, and we're going to revise the geomechanical parameters that we have to history match the model to those observations. Okay. So let's go back into our app. And we will blank everything by reloading, and then we will load in a new exercise here. So exercise 4 is the one that has this in. So what we've got here is a set of different representative reservoirs where we are going to iteratively change things to get a better match. So I'm going to basically walk you through doing that to see how we can zone in on a solution. The software itself actually has an optimizer built in. The 6X simulator itself has an optimizer built in that allows you to do automated history matching, but we're going to do this step by step with a few kind of representative numbers to show how changing something in the setup changes the results. Okay, so here's our plot panel. If we do import plot, we can bring in our historical observations, and they plot like that. Of course, usually we would plot those as points. So here's the historical rate as points. So it looks like we've got a plateau over to about here, and then it's falling off and gradually declining. So our job here is to change our input parameters so that we match this. Okay, so our first guess at what a reservoir should look like is here. By the way, the only parameters that we're going to modify here are the ones on the geomechanical setup, those enhancement parameters. Now, it may be that the underlying geology needs to be modified too, but just as an example, we're just going to use these ones here. So for step one, we're going to use a low compressibility and a high compressibility. So we've got 5,000 and 1,000 microsips. So we picked some arbitrary values for the enhancement in the permeability and the shear, and we're going to run with these and see what difference it makes to go from the compressibility of 500 to 1,000. So let's go load our results from those. So if we do get model status, and the ones that we want are one low compressibility and one high compressibility. So we'll load these two in. And we change those to lines so that they're clearer. So our high compressibility has given us a very short plateau and a gradual decline. Our low compressibility has given us a very long plateau. So if you imagine the more compressible the rock is, the more ability it has to move out the way and, for want of a better word, absorb the frac fluid that's inside the fracture volume. Yeah. So the more compressible the rock is, the less incentive there is for the frac fluid to move through to enhance the next piece of rock. It's a disincentive for propagating the fracture, if you like. So 500, which gives us this green line at the top, is clearly too high of a number, and 1,000 is clearly, sorry, excuse me, 500 makes the rock too hard, 1,000 makes the rock too soft. So we want something in between. Now I mentioned that we have an optimizer built into 6X for doing history matching and such. We also have the ability to run sensitivity cases with a range of values. And we can support that functionality from here inside the online app. So if we click on this one comp range version of the reservoir here, we have highlighted the compressibility as something that we're interested in using as part of a sensitivity study. So we highlight that, and then we go to our scenarios. Sorry, we go to our build, excuse me, sorry. and we look at the settings for one comp range on the sensitivity panel, and it's telling us over here, okay, you've got the compressibility available to modify, and we fill this out to tell it how to modify it. So we're going to say we want to go between 900 and 600 because we already tried 500 and 1000, and we know they were respectively one was too big and one was too little. So we're going to try 600 to 900, and we're going to try 4 samples between these points. Okay. So we build that, submit it. The simulator will automatically iterate through 4 separate cases, each one with a different value of the compressibility. And then we can go plot those. So if we do get model again, so the compressibility range is this one here. And we've got a set of line plots for the effect of those. We've also got some multiple realization output over here. And what that is it's a plottable summary of the parameters that we used. So if we put them all on at once, it looks a bit of a mess. But if we come in and we plot the one comp range, and we just plot the time on the axis and the oil production range, then we can see the different results we get there. So we've got the 4 sample values that we asked for, plus we've got the default value, which was the 1000 that we had typed in there in the first place. So there's our different parameters that we can get based on those inputs. We can clear that and plot the case name or the case number against the parameter value if we want. And that looks like this. So it tells us what case used what value. Okay. So based on these, we can make a decision. Whoops, excuse me. We can make a decision on which compressibility works best for us. Okay. So if we put those on and plot them all as lines, and we plot the parent well, which is the observed data, as points, then we can see in here where that fits. Okay. So we can go back and we can create, well, we can pick a particular value for our compressibility, and we can input that. Let's say we pick 850 based on those plots, and we can repeat the same kind of scenario with the tensile permeability add. So we've got a version where we've got a low end and a version where we've got a high end. So we've picked 600 and 900 millidarcies as the amounts that we're going to add. So we've already got those cases built, the 2 mid and 2 low tensile, and we can go plot them. So let's clear this from what we had before, replot the parent well, and get those 2 low and 2 high. And plot those as lines, and we should see, hopefully, that we're kind of bracketing the right answer. So we're getting close here. So the ones that we tried were 900 and 600. So let's give it a try with 750. So we'll stab in the dark, make a guess that that might be a good answer to use. So let's go plot that one. So we do get and load the 2 mid tensile. And voila, we hit it pretty close. So we got a pretty good match with those combination of numbers. Now, it may be that there are several combinations of numbers that also give you a good match, some of which are equally probable to be realistic, and some of which might be complete nonsense. So you need to put a little bit of engineering knowledge into here. You know, it may be that if I put compressibility of 10,000 and maximum permeability enhancement of 1, I could get something that looked similar. But you need to kind of use your knowledge of what's reasonable. So we've got a good answer here. However, we've got that good answer without really exploring the impact of our third parameter that we were going to talk about, which was the rubble generation, the shear factor. We had it at 0.2 initially, and it looks like we're quite capable of getting a good result with 0.2. But just for completeness' sake, we can go and use the parameters that we've selected so far, and we can plug in a range of values for the shear to get the sensitivity to it, to see how much difference it would make if it was, you know, higher or lower. So we select that parameter, we go to our build, and we say for 3 shear range, we want to set up our sensitivity based on the rubble generation parameter. And we're going to say we want a minimum of 0.1, a maximum of 0.3, and 5 samples. So we submit these jobs, we get those runs done, and we can go plot them. So let's see, we'll clear off these ones, and we will do get model and load up our 3 shear range. We'll just get the results. We won't worry about plotting the parameters. So this is the recovery that we get as we vary that. So if we say, show us just the last part of the run, maybe move in a little closer, let's say 1400. So here's the last stages of the run. Depending on what number we put in, it makes our recovery vary from 1.7 million to 1.88. So there is a bit of a spread based on what that parameter could be, but not a, it doesn't, they all look fairly similar if we zoom back out. Okay. So we've proven that we can vary the way that the fractures propagate to match a set of known data. So the things that we looked at were on the geomechanics parameters there. So the compressibility, as we said, it controls how rapidly the pore volume can change, how the pore volume expands. And the higher values allow the fracture space to expand quickly in response to pumping. So rather than the fluid being forced to move through the fractures, it can stay in one place and just push against the walls and occupy that space. So the higher values generally end in shorter fracs. Lower values, which is stiffer rock, causes the fractures to have to go longer. Okay. The tensile input controls the permeability, which is used to build the conductivity of the fractures. So higher values tend to make it easy for the fluid to stay in the fracture and move further out into the reservoir. The lower value will make it more difficult for that frac fluid to move away from the well into the rock. So a lower value permeability addition is more likely to result in leak-off. Now, the leak-off itself is going to be controlled by this shear input that we're giving, where the higher the value, the easier it is for the fluid to leak off. The lower the value it is, the harder it is. So this controls the effectiveness of the matrix fracture interface in terms of how to move fluid from the fracture to the matrix and then back from the matrix to the fracture. So the propagation of the fractures is a balancing act between these three parameters, essentially. And together they determine what length you get for the half length of the fractures, how conductive they are, how much leak off you get. One thing that we don't go into here is that the height growth and such is going to be relative to the relative magnitudes of the stresses that we put in, which is another potential unknown, or maybe you have a good handle on that. So these are the parameters that we can use to build our model from something which we can run in, and it doesn't match well, to something which is tightly calibrated and gives us a good way of then testing different scenarios for how we're going to complete the next well, or a well in an analogous section a little bit, off to the side or something like that. Okay, so that's an illustration of history matching. So we've shown how to do experimentation on the design parameters and how to calibrate, how to history match the rock to known observations. So those are the two examples that we're going to stick with for today. If you're interested in taking a look at 6Xonline yourself, there's a web address here, or you can go to the website and you can click on the 6Xonline information there. The website is here, and my name's Peter Foster. The guy who was talking at the start is Tommy Miller. He's in our UK office. If you want more information about 6Xonline or about 6X itself, you can contact us. And also, we're going to be having another presentation next month. And what we'll be looking at in that presentation is some multi-well setups within 6Xonline to explore questions like, how closely can I space my wells before the SRVs start interacting and interfering with each other? So that's what we'll be looking at next time. We're also, it isn't mentioned here, but we're also probably in April going to do a presentation on 6X itself, where we'll talk about the full range of functionality that it has, not restricted to the stuff which is available through the online setup app. Okay. So that's all I have until we come back with the next presentation.